Hello there, and welcome to the third video as part of this online tuition for Mechanics 2. Today we're going to be continuing looking at equilibrium and moments, but we're going to extend the problems we can do by examining forces which act at an angle to the whole system. Okay, so if the force acts at an angle to the object, then we have two options. Now, there's two ways you can do this. I always prefer it in one of these ways, which we'll see in a second, but you're totally legitimate to do it in either way. The first way is that we remember that the moment is based on the perpendicular distance from the line of action of the force. Okay, and I'll show you that in a second. The second way we can do it when forces are acting at an angle is that we can resolve the force into components perpendicular and parallel to motion and ignore the component parallel to the line of pivot. Quite long sentences, quite a lot of words there, but when it boils down to it, it's not so bad. So we've got an object 5 meters long, and the force is acting at an angle of 30 degrees, and it's a 50 Newton force. Okay, how can we calculate the moment of that? And we're going to have our pivot point here. Okay, now the first way is that we remember that the moment is based on the perpendicular distance from the line of action of the force. Now this is I don't prefer to do it this way, but it's perfectly fine. If we extend the line of action of that force, okay, and what we're after is the perpendicular distance. Okay, so we're after that length there. Okay, so that's perpendicular, it's 90 degrees. We can, because that's a 90 degrees, we've got a right angle triangle here. So this distance here is going to be, well, it's that the hypotenuse is 5. It's the opposite of the angle, which is 30 degrees. So it's going, that distance there is going to be 5 multiplied by sine 30. Okay, so the perpendicular distance to the line of action of this force is 5 sine 30, so the overall moments is 50, the force, multiplied by 5 sine 30, which is 125 Newton meters. Okay, that's one way of doing it. My preferred way, however, is to, and because I think it just gives us a little bit more information, it can help us with other problems, is to resolve the forces into parallel and perpendicular directions. So in this case, we've got the 50 cos 30 and the 50 sine 30. Okay. Now I just think this is easier because then we know that because the parallel, this 50 cos 30, we know that's just going to completely disappear anyway. It's going to completely disappear because the line of action runs through the pivot point. So once we've done our resolving, we know that the size of the force is 50 sine 30, and we're multiplying it by 5. The distance, the perpendicular distance, it's clear that 5 meters is the perpendicular distance. So it's 50 sine 30 times 5, which is again 125 Newton meters. I prefer to do it this way. I prefer to resolve forces, and then you can just treat them as normal. You base the problem as normal, and you don't have to write all dotted lines and figure out distances and everything. And the distances will already be in the question. So let's do this in the case of an example. So what we've got here is we've got 4 tugs maneuvering a ship. Okay, so this red thing is a ship. We've got 4 tugs maneuvering it. A and C are pushing it. So let's have a look there. A and C are pushing it. A with a force of 8,000 newtons, C with a force of 3,000 newtons. B and D are pulling it through a rope, and that green dotted line is a rope. At certain angles, 45 degrees and 10,000 newtons, 60 degrees and 14,000 newtons. It says, find the resultant force and the overall turning moment about its center point 0. Okay, so there's its center point. It's halfway up, so 15 meters up, and you can see there it's all cushy. So let's get rid of these diagrams. Let's change them into forces because becomes a bit of a nightmare otherwise. We don't draw pictures of tugs and everything. So let's change these into forces. Okay, right. This makes things a lot easier. Now, this force here, let's get a little pen here. This force here and this force here are already acting at right angles or parallel to the object. These are the two forces which, this one here, which are acting at angles. So my first port of call is going to be to resolve these forces into directions perpendicular and parallel, okay, at 90 degrees, which isn't too much of a problem. So that one there, okay, it's going to have that as its resolve forces. 10,000 cos 45 going vertical, 10,000 sine 45 going horizontal. This one here, it's going to have 14,000 cos 60 going horizontal, 14,000 sine 60 going vertical. Okay, so to find the resultant force, if we take the positive direction as vertically upwards, we can see our forces going vertically upwards are this 8,000 plus 10,000 cos 45. But to find the resultant force going vertical, we have to subtract the 3,000 and the 14,000 sine 60. For the horizontal, if we take the positive as going right, then it's 10,000 sine 45 minus 14,000 cos 45. Okay, put that into a calculator. You get 10,000 over root 2 minus 7,000, and that eventually works out as 71.07. So the resultant force horizontally is going 71.07 in the positive right direction. Okay, so for the vertical, what we said, it's got the 8,000 plus the 10,000 cos 45. That's what we've got there, and going downwards, vertically downwards, so it would be negative 3,000 minus 3,000 minus 14,000 sine 60. Put that into a calculator, we get minus 53.29. So our resultant force is actually going to be, well, if that is, because it's negative, in the vertical direction, it's going to look something like that. So our overall resultant force is going to be somewhere in the direction of southeast. Okay, the southeast direction somewhere. I can't work out the angle, but if that's 71, well, we can work out the angle. I'm not going to bother with that. 71.1 to 3 significant figures, and if that's 53.3 to 3 significant figures. So to find the resultant force, find the size of the magnitude, we have to use Pythagoras' theorem. So the size of the force is 71.1 squared plus 53.3 squared. Take the square root, and our resultant force is 88.83 newtons. So it's going to go in this direction here, with a size of the force 83.83 newtons. And we could actually find the mass of that and the acceleration if we wanted, because if we know the mass, we can find the acceleration as well. Okay, so we found the resultant force. Now let's find the resultant moments. Okay, to find out what kind of angular motion this boat will have. So because we've already resolved the forces, it makes our lives a lot easier. Okay. Now let's have a look at the clockwise moments. Now these are the arrows which are going to go around in the clockwise direction. Now it's going to be that one there, okay, because it's round. If we take the pivot point as the center, you know, it's going to go round like that. That's nice. That one there is going to be clockwise because that's going to go round like that. And that is it, actually. They're the only two clockwise moments. It's going to be that force, this force here, that's going to contribute to a clockwise motion, and this force here, which is going to contribute to a clockwise motion. Now, you may wonder why I'm taking it about the center point. It's because asked us to in the question. Now, the perpendicular, we need to get some lines of action because it's the perpendicular motion. This shouldn't be too bad because for this one here, the line of action continues that perpendicular distance there. Well, that's just literally 15, okay? And the same for this one, perpendicular distance from there to there, that's going to be 15 as well. So it's going to be the moments clockwise are 15 times, or 10,000 sine 45 times 15 plus 14,000 cos 65 times 15. Okay, which is what we have there, and that's equal to 211,066 Newton meters. Okay, now let's examine the anti-clockwise ones. Now this is not a problem. We'll pick them out because they're all just the ones which we've got left over. Okay, these are all the anti-clockwise ones. Now, if we take these ones here, well, the line of action is this line here, both of those forces. That's 70. So we're going to have 70 times 3,000 plus 70 times 14,000 sine 60. We're also going to have a plus, well, this distance from here to here, this line of action is 50, so plus 50, 10,000 cos 45 plus 50 times 8,000. Okay, so there we have it. There we have all of those calculations, which you can put in a calculator, and we get 1,812,258 Newton meters. Now, if we take anti-clockwise moments to be positive, and the clockwise moments is negative, the overall moment is going to be 1,812,258 subtract 211,066, which is approximately 1.6 million Newton meters. So, yeah, there's the resultant moment going clockwise, anti-clockwise even, 1.6 million Newton meters. Okay, let's have a look at a different situation, or let's adapt same situation, but let's add something else to it. Okay. A breeze starts to blow from the south, causing a total force of 2,000 newtons to act uniformly along the length of the ship at right angles to it. How can the tugs A and C counteract this while maintaining the same overall turning moment? Okay, now let's interpret this question, because basically it's saying the turning moment is the same as before, so it's 1.6 million Newton meters going anti-clockwise. It doesn't say anything about equilibrium. It doesn't say anything about resultant force being the same. All it's saying is that the overall turning moment is going to be 1.6, okay, Newton meters. Okay, now because of that force of 2,000 newtons, the force at A, we're going to call that X, that's going to change. And the force at C, we're going to call that Y, that's going to change. And we need to find out what X and Y is. Now, this total force of 2,000 newtons, it acts totally along the length of the ship, so it makes sense to say that it acts at the center point there. Okay. Now, to maintain the same overall moment, X and Y have to change. We have to find out what that is. How do we find out X and Y? Okay, so there's our information, there's our forces. Now, first of all, it doesn't really make much sense now to take overall moments about 0, because we're going to have an equation involving X and involving Y. We want to have two equations because we've got two unknowns. It makes sense to take the moments about here and about here, okay, at these corners, because that will eliminate one of the variables. So let's take moments about C. So let's take our moment and change the ink color to yellow, orange. We're going to first of all take moments about this point here, because that will eliminate a lot of the forces. It's going to eliminate Y. It's also going to eliminate this force here, because this force here is the line of action lies on the pivot. Is there going to be any other forces it eliminates? Yes, it's going to eliminate this force here. Okay, because this line of action of this force lands on the pivot. So let's go clockwise from this point. Now it's going to be this one. This one's going to be clockwise, and that's a moment of 30 multiplied by that. Are there any other clockwise? Well, this one as well. The force of the wind. This is going to be clockwise. Okay, because that's going to be going around like that. So yeah, they're the only two which are going to go clockwise. Yep, these two are going to go anti-clockwise. So it's going to be 50 multiplied by 2000, which we've got there, and then we're going to have 30 multiplied by 10,000 sine 45, which we've got there, and typing that into a calculator we get 313,132 Newton meters. Okay, so that's what we've got clockwise. Anti-clockwise, well, it's just these two forces here. We've got this xn and we've got this 14,000 sine 60, and they're both going to be multiplied by the distance. The perpendicular distance is 50 plus 70 is 120. So we've got 120 times 14,000 sine 60 plus 120 times x, and that equals 1,454,923 plus 120x Newton meters. Now, we know that the overall turning moment has to be 1.6 million. So we can set up an equation where this quantity subtract this quantity is equal to 1.6 million. Okay? Now, a very easy equation to solve. We can just add this quantity to both sides, subtract this quantity to both sides, then divide by 120, and we end up with eventually that x is equal to 3,800 newtons, the two significant figures. Okay, going well. We've just found moments. There's an unknown. It's not going to phase us. We just set up an equation. Pushed it. Now let's have a look. We need to find y. Now, by putting the pivot point there, we got rid of y. Let's get rid of x now, even though we know x. Just makes sense to make it easier. Let's take our moments about a. If I take our moments about a, it's going to eliminate that force there, which is nice, because that is on the line of action. It's going to eliminate the xn, obviously, as well. Are there going to be others? It's going to eliminate this force as well. So, let's take moments about a, because it will eliminate x. Let's take the clockwise. Now, which ones are we going to get clockwise? Which ones are we going to get clockwise? Well, this one here is going to be clockwise. It's going to go round like that. This one here is going to be anti-clockwise because it's going to go around like that, as with this one here and with this one here. So actually we've only got one clockwise moment, which will be the distance 30 multiplied by 14,000 cos 60, which is 210,000. Yeah, 210,000 Newton meters. Now going anti-clockwise, that counts for this one here. So that's 70 lots of 2,000. We're also going to have 120 lots of y. We're going to have 120 lots of this 10,000 cos 45 as well. Okay. So 120 times 10,000 cos 45, that's this anti-clockwise moment. 120y, that's that anti-clockwise moment. And 70 times 2,000, so that clockwise moment, which simplifies to 988,528 plus 120y. Again, we know the moment, the overall moment, it doesn't matter where our pivot point is, our overall moment is going to be 1.6 million Newton meters. So it's this quantity here, subtract this quantity is equal to, well, I've got 600,000 there. There's obviously clearly a typo. Okay, 1.6 million. Again, by adding this quantity, subtracting this quantity, we get that y, and finally divided by 120, we get y is equal to 6,800. Okay, so that's it. Yeah, by using moments at an angle, we've calculated some forces and some unknowns. I think the best strategy is to, whenever you get a force at an angle, declare your positive J. We haven't really done that because I don't think, with Mechanics 1 it's important to do it, but Mechanics 2 should be obvious where it is. But define your I and J and resolve all forces. That's straight away. As soon as you see a problem, define your I and J, resolve all the forces into directions in the I direction and the J direction. Just do that instantly. Then the problem, you eliminate the problem of any angles, and it's just taking normals, taking resultant forces as normal. Okay, so what I'd like you to do to finish off this chapter on moments of force is to attempt exercise 3B. That starts on page 46. So page 46, and have a go at the questions there. Okay, have a go at the questions there. This question is actually taken from that exercise. It's question 10, so don't do question 10. But for the next couple of lessons, we'd like to practice those questions there. Brilliant. Thank you.